Happy Friday, everybody. So today we're going to go through the next chapter in our discussion of kinetics. This is bridging off of last time. We've discussed the differential rate form, right? Rate laws, talking about the change in concentration over time. We then talked about integrated rate laws. This is our way of using something like our rate equation or a rate law to predict what concentration we expect at some future time point, given a certain rate constant, given a certain order in reaction, okay? And we talked about a couple different classes. Remember, the integrated rate law looks different depending on the order of the process. Now, this is the overall process, right? We talked about we're going to discuss three basic orders of processes or orders of reactions. What are your three common orders of process, order of reaction? We have first, we have second, and that's right. So we discussed first. First is the most common. That's what you'll see quite a bit. We often start off by assuming reactions follow first order kinetics overall. Now, oops. So remember, once we have the integrated rate law for a first order process can look like this. It's the logarithm of A at some concentration time is equal to minus kT. K is your reaction constant. T is what? This little t is? That's time, exactly. And then ln A0, that's the concentration that you started out at. So your initial concentration at some time t. Okay. Because we can express it this way, this is in the form of a linear equation, y equals mx plus b, which means if we're looking at a plot, we're on the y-axis. We have logarithm a. We're expecting a negative straight line, where the slope of that line is our minus k. It allows us to very quickly extrapolate what the rate constant should be, provided it follows a first-order process. We discussed a second-order process. Again, when you look at the concentration versus time curve, the first thing that should jump out at you is when you're looking at that. That's our native one, right? That's if I set up for a reaction. Usually, you're following concentration in time. You don't necessarily know if a reaction is first order, zero order, any component. You're just usually starting off by mapping how does concentration change. And if you notice, first order, it's got this gentle, soft landing. I would say that a first order is kind of if you imagine you're in an airplane, this is an okay descent, right? This would be how you might land, where you kind of come down fast, and you've got this nice, gentle landing at the end. This is more of like a roller coaster. It's much steeper initially. Oops. Yeah, second order process has a sharper decay. This would not be something that would be a comfortable landing, particularly because you've got this massive plummet at the beginning. Why would that be? Why is the reaction so much faster initially, and then it kind of way slows down? How if you had to sort of express that or tell somebody that, why does that make sense?
You need proportionally more fuel compared to the product.
That's one way of thinking about it. Remember, what we're talking about here, the rate equation for a second order process will look like this. Oops. Well, this will work. Rate for first order process is K times the concentration A, which means if A is cut in half, the rate is cut in half. If A is doubled, the rate is doubled. There's a one-to-one relationship between the two. In a second order process, rate is equal to K for simple thing, A squared, let's say. That means a tiny decrease in A will have a much larger decrease in rate. If you half the concentration in A, what happens to the rate? 1/2 A equals what to the rate? 1/4, right? There's a we can drop this much the rate slows down so much more because it's so much more sensitive to the concentration of A. The other way you can think about it when you're actually in this very latter part of the curve. Nope. The reaction, as you get close to the end of the reaction, A is looking for a partner. And as you start losing, or you're low on the concentration of A, it's looking for its dance partner. The concentration's low. It's going to wait and wait. The reaction slows down because it needs that second component of A. If you're on the second order one, it has this flatter point. So visualization, you should be able to kind of get a sense of it has this precipitous drop. That's a second order. Softer landing, first order. Much easier, though, when you go to your linearized one. If you take the integrated form of the rate law It's now 1 over A is equal to positive KT plus 1 over A naught. That's our structure for y equals mx plus b. So plotting now 1 over the concentration on our y-axis and time on the x-axis, we get a positive straight line between here. Now there's one smaller complication, still kind of second order-ish. Now we talked about the specific case for second order rate where A reacts with A, right? That's how we get this simple numerical derivation where it's Ka squared, where you're basically reacting two molecules of the same thing. There are other second order processes. What if we had something where the rate was equal to K times A times B? Different materials. This is just useful because I can independently manipulate the concentration of A and B. If it's dimerization, A squared, adding A reacts with A, it's always second order. This is still a second order reaction, right? The rate law says K times A times B. What is the order in A for this guy? What's the order in B? Overall, second order process, right? We discussed last time, if I were to graph this, imagine that A and B had exactly the same concentration. So imagine a case. We start off with the rate equation is rate is equal to K times the concentration of A times the concentration of B. And we start the thing where the concentration of A, let's say, is equal to 0.1 molar. Concentration of B is equal to 0.1 molar. If I was going to sketch this graph of simply concentration of anything, so any species, versus time, so just conc. Remember, this is a second order overall reaction. It is first order in individual components. But what should the process look like? How fast or how steep should this curve drop? Will it look more like a first order reaction or more like a second order reaction? It's first order in component, but overall, when we graph this, concentration versus time, we're watching the order of the entire process. So this will look like the concentration of product will have a steeper rise and a flatter tail. This kind of looks second order like. The reason why is because it needs two things. They're different things, A and B, but second order overall. Remember, I cannot determine the order in one component from one reaction. The process, I can. If I were to graph this, the 1 over concentration, I should get a second line positive slope. It is a second order process here. And again, that's back to if I were to graph, let's say, A going away, it would have a sharp curve like this. B going away, if that's the same one, they're just going to walk the same point. The concentration of B and the concentration of A are going to have the same overall profile that overall is following what looks like a second order process because it obeys the order of the overall process. It's a second order overall reaction, therefore its concentrations will come out here. If I needed to find out for sure, it is first order in A. What experiment do I need to determine that the rate law is first order A, first order B? I was way back on Monday. What do we do for that? That's called a method of initial rates, right? I would set up an experiment with some amount of A, some amount of B, measure the rate right when I start the reaction. Change what I do to A, double it, and if the rate doubles, it is first order in A. I do another experiment, first order in B. But those are a series of experiments to tease out what the individual orders are. What we graph when we talk about these graphical rate laws is the overall order in a process. But this gets complicated. That's what I just showed here. The math is the same as long as A and B have exactly the same initial concentration. The integrated rate law follows the same point. If it is not the same, the math gets more complicated. We still use up 1A and 1B, but it's much harder to talk about an integrated rate law if these are not the same thing. So usually, experimentally, we do something where we say, okay, we're going to simplify things. This is like dealing with our closed system or any of the other, constant volume temperature, constant volume heat. We're going to set the conditions that make our life a little bit easier to make a measurement. We're going to say, I will use pseudo first order conditions. All we say there is, okay, I know the true reaction obeys the law shown there. First order in A, first order in B, second order overall. But what I can do is I'm going to pick initial concentrations for one of those two such that they're very high compared to the other. As a result, one of those two concentrations is not going to change very much. It's a constant. What we do is we bias the reaction where instead of saying both of the things can be driving the bus, there's a fight of who's running the show in terms of A and B. If there's a ton of A and only a little bit of B, as the reaction runs, the concentration of A doesn't change that much. In other words, the concentration of A almost is constant. So if we do that, this equation gets a little simpler. Under pseudo first order conditions, I know the reaction is second order overall, but I choose something where I'm saying, okay, the concentration of A, I'm going to make it really, really, really high. And the concentration of B, much smaller. And as a result, concentration of A does not significantly change. I'm going to assume it's constant. And now that simplifies the equation. Sorry, the example I've shown up here, I've actually done the opposite. I'm going to make the concentration of B very large to be treated as a constant. So what I'm saying is that here, delta B versus delta T is approximately equal to 0. It doesn't change that much. I'm not saying that the concentration is 0. I'm saying the change in concentration is 0. It stays the same. So if we consider that this value is a constant, I get a new, what we call pseudo rate constant. It's a pseudo first order rate constant we call K prime. K prime is just the actual rate constant from here multiplied by the concentration of B, held constant in this reaction. So this gives us a way of isolating the reaction and studying it with respect to only A. I hold B constant, I can see what A does. And then I could flip around and do the other side. I could hold A constant, see what B does. The important thing is, when you use pseudo-order conditions like this, the rate constant you solve in this process will be the rate constant, true rate constant, multiplied by the concentration you're holding constant, the concentration of B. If you did this, so we've taken what used to be a second order process. I hold B super, super high in concentration. Its change doesn't really affect the rate now. It going down will not slow the reaction down. You've got as much fuel in B as you want. So now it obeys this new rate constant here. This is the visual, or this is the observed rate constant you'll see. If it's now obeying this second one here, is this a first order process, second order process, zero order process now? It's first. We've made what used to be a second order overall process. We hold B super, super high. It becomes a constant. Now it obeys a first order. In other words, if I were to graph this, it's going to look like the concentration A against time will look like a first order process now. Yeah? That totally depends on how much A you have and that rate constant. The sort of rule of thumb, if you're going to go to the bench, 10 times is good. There's a whole other dark art to this. The reason I got into kinetics, and this is something I fully profess to all you guys, in first year, all we do is lie to you. Sorry. No, we like to present it first because this is a conceptual way to understand. Look, I had complexity. It's first order both. That's really hard to deal with. I'll make the math simple. I'm going to now hold one constant. That reduces the complexity. I can study it. This works pretty well for very simple systems. But the second you actually get into, like, there was a case that we got involved in. And I say case because we're like CSI, but there was literally, industry came to us and asked, this is what's going on. We've made these assumptions. Nothing makes sense. And the problem is, sometimes when you do this, what do you think might go wrong if you do this? I'm holding B super, super high concentration. I'll make A low. I'll study the system. That's a good model. What do you introduce if you do this? A lot of error, but what do you think might go wrong if a normal day-to-day was A and B like to play in roughly equal ratios? That's how they are in the wild. Then you take this wild lion, you say, I'm going to study it. I'm going to put it in a cage, and I'm going to wrap it around. I'm going to feed it steaks 3 times a day, and I'm going to study how it behaves and say, that's probably how a lion actually is in the wild. The second you perturb a system this far, sometimes this is great, but it has no bearing on the real system because so much B can now react with B. You've got so much B can play with everything else. It's doing all this other crazy stuff that would never happen in the normal world. Sometimes the approximations we make introduce all kinds of new errors. So this is a good way to start, but yes, if you're interested, there's a lot more to do after this. Anyway, the method of pseudo first order is the best thing we have right now with the tools that you've got. It allows us to simplify a system, but the most important is what used to be a second order process is now a first order process because we've made one of those values constant. Okay. The last one. So we have our first, we have our second, we have our special case second, that's reduced to pseudo first. Last one is our zero. If we had a reaction, A plus B goes to C. And let's say for that one, it obeys this rate law. That the rate of change of A is just equal to K. Nothing else. There's no other terms after that. There's no concentrations. It doesn't care how much A you have, how much B you have, how much C you have. It will just hammer along according to the rate. Disappearance of A versus time is just equal to a constant. Can you think of a process that might match this? What is something that you consider a zero order process that you might have experienced? Really strong, no, that's still, remember, this is fast. Really strong acids are very quick. Their rate of reaction would still definitely depend on how much you have. Zero order is something that just is a juggernaut. It doesn't care how much concentration it is. The rate will always clock along regularly. Yes? Still again, does a fire get smaller as you run out of fuel? Yeah, so that's not. What else? Again, this is something that does not, like it is unstoppable, clicks along. What's that? Rusting is pretty good. That's getting close. Rusting just happens under the right conditions. And it doesn't really matter how much air you have because we have so much air. Like the amount of oxygen is so high. Effectively, yeah, it does matter how much oxygen you have, but it's kind of like the pseudo first order problem we did. As long as one of your concentrations, your things, is so large, its concentration doesn't really change, your car will rust at the same rate no matter how much oxygen is in the atmosphere, more or less. That's a good point. Yeah, what else?
Autoionization of water.
Yeah, well, again, autoionization of water will depend a little on temperature, but good, again, because it's a physical constant. The one I like to go to is photosynthesis. As long as light is on, plants will produce sugar at a rate that's based on just how much light you give it. As long as light's constant, it just clicks along and produces sugar. Again, CO2 is being used up, but there's so much CO2, it doesn't make it go faster or slower. These are a little bit harder to see because we're not used to seeing things that just happen, right? That is a zero order process. Well, but nice thing is, the math gets much easier. The integrated rate law of dA dt against a constant is just the concentration of A at some time is equal to minus kT plus the concentration at T0. That means this is our overall one. And once again, if you know it's a zero order process, knowing the constant and how much time, you can calculate where you're going to be, your landing. What this looks like graphically is very simple. Now the normal concentration versus time graph, nothing, the y-axis is just concentration versus time. Not log concentration, not 1 over concentration, just concentration versus time. And that already is in the form of a linear equation, right? So if I actually go here to my integrated rate law, my y value is my concentration, my x time, and since I've expanded over here, my slope is my negative k value again. So we have 3 plots that we're used to looking at. A first order plot, negative slope, from log concentration, natural log concentration time is my K. 1 over concentration on my y-axis, my slope positive K, that's how I extract it. In a 0 order, just concentration versus time is a straight line. Negative slope is my, my K value. So those are your 3 fundamental graphical tests for the different ones that you've got, okay? So looking at those axes will help you. Now there's one other point that we have to talk about. It's what's called half-life. Half-life, so who's heard of half-life? Is it in the context of a game?
Yes.
Okay. Still, what was the thing about that? Why was half-life relevant for the game Half-Life? Like, it's, what about it? Right? Yeah, nuclear disaster, radioactive decay. That's not normally where we hear half-life, right? Why does that matter? Like, when we talk about the half-life and something about Chernobyl, why does this matter? Yeah.
Because it's so large, it takes forever to decay.
Exactly. So what we're talking about, half-life is the amount of time that it takes for a concentration to reach half of whatever it used to be. It is a relative value. So if you said, I have a process, I have some amount of material in solution, I can define what the half-life is if I know how fast it reacts or decays. And why this matters for radioactive decay is that, yeah, radiation is toxic to all of us, most of us. I've been in the lab long enough, I think I'm semi-immune. But effectively, it has to decrease to a certain level. It has to be down by a certain amount. If I start with a whole bunch of radiation, and the half-life is 50 years, we're saying that it will take 50 years before the radiation drops by 1/2 of wherever it is now. And then another 50 years to be half that again. And again, this could take forever to reach certain levels. Now, what's really interesting and why these things become, like, that's the definition of half-life, half of whatever you start. Because different ordered processes have different integrated rate laws, their half-life equations look different. So, in a 0 order process, what we can do is we take the integrated rate law and we can express it and say, this is the half-life equation for a 0 order process. This is the half-life equation for a 1st order process, and the half-life equation for a 2nd order process. Do you guys notice anything special about 1st order? That's right. 0 order processes have this term here, A0. What is A0 again? The initial concentration. 1st, 2nd order, initial concentration. 1st order processes are special because their half-life equation does not depend on initial concentration. It's just a constant. Ln T, right? That's math. K, that depends on the species. And then your half-life. Half-lives of 1st order processes are really useful because I don't need to know how much I used to have. If I know a process follows a 1st order process, I can say, I can measure it right now, how much do I have? And if I know the half-life, I can extrapolate and say what I used to be. I can also predict anywhere in the future. Just knowing K for my 1st order process allows me to actually visualize everything about this one. That's how carbon dating works. If we assume that I know the half-life of carbon-13, I can measure what I have now and then extrapolate back to what it should have been and put a time on it just because I know K. For a radioisotope, for this is what we do with Chernobyl, if I know it takes this long, the half-life is blah, I can predict with really good certainty how long I have to wait until the value reaches a certain level. I don't need to make a really accurate measure of how much I have right now. I can just say, look, this is how long it'll take to reduce by half, 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 half. 2nd and 0, we do have this consequence. So this one looks graphically, right? If I have a 0 order process, we're saying that the concentration versus time follows this straight line. If I start with some amount, let's say 1 molar. So if I'm up on the y-axis, I start with 1 molar, it will take this much time until I'm half that value. That's my first half-life event. Then from here, I'm now at 0.5 molar to go to the 2nd half-life value. I have a new time, 3rd half-life, new time. Like notice, each time, the amount of time I have to wait before the concentration reduces by 1/2 is getting smaller. It's compressing. Why? Because it doesn't care how much there is. It's just sauntering on like a Sherman tank. So the half-life values keep getting smaller, they compress. Second order, you're constantly waiting longer. The first half-life happens very quickly. To wait to get to the second half-life value, it's a longer time. The third half-life value, even longer. And that's, again, you've got this 1/over relationship with the initial concentration. As the initial concentration drops, the half-life value gets larger. They're inversely related to each other. This is also why if radioactive decay followed second-order processes, it would just keep getting worse. Yes?
Does it ever reach 0 for first and second order?
So theoretically, no. It's a limit function, right? Now, again, that's an approximation. Obviously, it eventually has to. And that's what we call terminal kinetics. That's what happens in the very low levels of it. So this is what's called steady state kinetics, what happens in the bulk of the reaction. Little different things happen here, but you're right. Mathematically, it never actually reaches 0. In a first order one here, that's exactly it. Half, half, half. The spacing is always the same. It's a constant. And as a result of that, each time, each half-life we go through is a nice reproducible value. So they're great. This is what we like about them. This is what we can use them. If we know we're dealing with a first-order process, it's very convenient. That's why we use pseudo first-order processes, to simplify things. The other big one we use is a metabolism in pharmaceuticals. A lot of the times when we take something like a drug or something like that, your body metabolizes it according to a first-order process. And the reason why is there may be an enzyme that catalyzes it, but generally the concentration differences we're talking about take really complicated metabolic pathways, and it actually compresses it to look like a pseudo first-order process. So let's calculate this. If you know the half-life of some pharmaceutical is 64 minutes before it is now down, that's the first sort of half, and we know it metabolizes according to a first-order process. What is the rate constant? What is the K value of that? So, if we know we're dealing with a first-order process, we're saying that the natural log of A at time t is equal to minus kT plus natural log concentration A. That means that's what we're expressing. We say it is a first-order process. We could start directly on this one and derive it. But because we say, look, I know my half-life, I know it's a first-order process, I can immediately invoke the half-life equation. T1/2 for a first-order process is equal to natural log of 2 over K, the rate constant. I don't need to know anything about the initial concentration of the pharmaceutical. I just need to know my half-life value and K, one of those two variables. So I've been given my T1/2. It's 64 minutes. Natural log of 2 over K. So K is equal to natural log 2 over 64 minutes. If we evaluate that out, 0.0108 per minute. So once again, this numerical value, your time unit, is what defines what your time unit is for your first order value for K. Remember, if this was a second order rate constant, what would my units of K be? It would have, yeah, a per mole value into it. It's a first order rate constant. All we have is this concentration of time, and just time into that point. Yeah?
You wouldn't need to change K to like a second value.
Up to you. You know, so this is a correct representation of it. It could be expressed in terms of years, months, whatever sort of unit of time that point, just depending on what the convention was. You may be asked, okay, put it into seconds, in which case you'd reduce it through those 2 points. So again, that's the convenient thing about knowing if it is first order, and you know the half-life, one of the things, either the T1/2 or the rate constant, you can get the other component. This is also why we can do things like carbon dating, where here what we know is the rate constant. We know how fast carbon-13 decays, and we know what it should have been, how long ago the concentration should have been. We can use that value to put a time onto an axis, how fast we go back up. This is in this radioactive decay piece. This is where, again, if we knew that right now the amount of radioactive material, call it 100%, is some amount. We know the half-life is 5.26 years. And then we make a calculation. How long will it take, given that half-life, to reach only 3.125% of that initial sample? Right? We're trying to wait. What is the time it takes to reduce it to this level? There's two different approaches you can take on this. So we can either, so let me go over to my other slide. We know T1/2 is equal to 5.26 years. We are currently at, you can say your A0 value here is equal to 100%, whatever that value is. We've got all of it right now. And we're trying to solve the amount of time before we reach A at time t, we don't know this value, is equal to only 3.125% of this initial value. So this is, again, if we were trying to carbon date something, we were saying we know what the ratio should have been, we know what it is now, we're trying to solve a time. So it's a two-part problem. Okay. So one way of doing this is saying, okay, how many half-lives have passed as a multiple? What I'm saying is if I'm at 100%, after one half-life, what percentage should I have left? 100% becomes 50. Then, so if you look at it graphically, you can say, all right, this is 100%, right? This is all the beans. After one half-life, I now have, this is gone, I have 50% remaining. That's one half-life. Second half-life, how much do I have left? It used to be 100, it's now 50. Second half-life, I'm down to 25% of my original value, right? Third half-life, cut it in half again, I'm now down to 12.5%. And then the third time, how much? Yeah, and then we do it one more time. 3.125. Oh, look at that, magic number. So this is, again, this works out nicely, but Meiji, what we're saying is I can divide out the amount that I've got based on what I have in this half, like halving each component. This works out to 5 half-lives later in the future, right? And again, it works for fractions and stuff either. This is one way people like to sort of do it is, okay, how many half-lives have I gone through? That value is it's 5 times T1/2. What do I need to do? If I work that out, okay, one half-life is equal to 5.26 years multiplied by 5. I get 26.3 years off of that. That's one way. Let's do it the other way. Oops. So again, we know the half-life equation, right? We're saying that minus kT is equal to natural log of 2. That's another expression. Remember, what we gave you was T1/2 is equal to natural log of K. Sorry. This is, I was setting up a different one, but that's what we got. So this is our half-life equation. What we can do, though, is if we expand this back into our overall, right? If we're trying to say that, look, if there's a first-order equation, we'd say log of A at time t is equal to minus kT plus natural log concentration A. That's our overall first. What we're really trying to do is figure out, I start off, A0 is 100%, and I'm becoming 3.125%, right? The reason I'm expanding it back to this overall is because really what I know, the information I'm given, is based on an initial value, A0, and a final value, I have A0 and AT. I'm trying to figure out my time that went in between these two. So with this, I know that my T1/2 value fits this classification. I could actually calculate the K value from that and plug it back into the overall. The other thing is I can work out the ratio that comes from this just by manipulating this equation here. The other way I can express this is minus kT is equal to, again, these two components. If I take those two lns and crush them together, that's like expressing this as ln of a at time t over a at time 0. Subtracting the two logs is the ratio of those two logs, right? So if I express my normal first order race equation like this, I've got these two values. I can say a at time t is equal to 0.03125. A at time 0 is equal to 1, right? So I'm expressing it as 100% is my 1 value, 3% of my 100, 0.0135 numerically, or the ratio of the percentages. So if I put that part through, I know my t1 half value for this point. I know my k value for this one. If I use this equation here, I can solve my k value for this one is equal to 0.13178 years. And again, how I do that is I know going in my t1 half is 5.26 years. Ln 2 over k, I can solve my k value first. So I start off by saying, I know my half-life. From my half-life, let me extract my k. That's a unit value for this expression. Now that I've got my k, I can go back to my first order process and say, I know how much I start with. I know how much I'm going to. That's these two values here. I need to put in the k of the process to solve for some new time. This k value comes from, this k value comes from my half-life. The value I do not know is how much time must elapse for this new change in concentration here, a at t0, a at t, and for this 3%. So using that, we can calculate through and extract our k, our t again should equal to 26.3 years. So what's useful about this ratio is it works for absolutely anything. It just requires you to use your half-life value to extract a k. Once you have that k, you go back to some new ratio, not just half, just A0, AT, for any new concentration. It can be any new value. And I can put these two into here to solve for my new time. Okay. So, as we said, two ways to look at this. Either I start with 100%, and I calculate how many half-lives might I need to drop to some value. Yeah, sorry. Yeah, exactly. You could. You're looking at, in the end, if all you have is a t1 half, you know a relationship for this halving value. You need to sort of pull back to your parent concentration somehow, your parent k value. As soon as you know that, you can extrapolate through, again, what that curve should look like, the differential, in order to extract to this point. Same thing. What we're doing here is we're using that integrated form back and forward to get through the constants. Both are true, yep. So first one is, again, how many full half-lives must I do to get to my target value? This is very convenient and fast if your target value is a nice, clean, whole number multiple of whatever it is, right? The other way, step one, start with your half-life equation, calculate your k moving forward. So here you have a direct relationship between a time you know, a t1 half, and your k. So you extract your k, then you go into some unknown value. This ratio here, again, just comes from your first order equation. We put in our two values for A0, A0, as defined by our percentages, put our k back into it, solve for the new time that we get from it. Both are different methods you can work through. So in summary, these are everything that we need to know. First order, zero order, second order. And we've got our different integrated rate law forms and our half-life forms that go along with it. Remember, down here it gets a little more complicated. What was the difference between what we called K1 and K2? Or this 2K1, 2K2 for second order? Remember, second order rates, you can talk about either in respect to the starting material going away, dA dt, we can define the rate in that way, or this here, this 1/2 dA dt, that's how fast your products are coming in. Since your products are half as fast as your starting material going away, when we have this factor of 2, We have this two different sort of versions of it. In the end, this 2K1 is just double whatever the value for K2 is. Again, the response this happens is if you're given a rate, second order, from the perspective of the starting material, you'll be solving this bottom rate equation here, dA dt. If you're given a rate from the perspective of the product, you're going to be solving this here. These two values for K, same thing, just multiples of 2 each other, just based on which side of the equilibrium you're looking at. All right. So what we're going to get into now, the really cool part of this, is how we apply rate equations. So we've talked about, again, predictive concentrations. We've talked about using these values to understand components. Where this becomes really useful is understanding the path, how you go from one starting material to another. So if you look at these 3 things shown out here, we have 3 reactions. Each of them uses hydrogen reacting with iodine, bromine, or chlorine. Quick question, are these all in their standard states? Hydrogen as a gas? Okay, bromine as a gas? No. Chlorine as a gas? Iodine as a gas? Okay, good job. You guys crushed it. I hope you had that on the midterm. Okay, quick question. Are these all strong acids? HI, HBr, HCl? Yeah, these are all strong acids. Which is the one that should kind of follows in this series that is not a strong acid? That is HF. Yeah, remember, dissolves people, not strong acid. That's right. The important thing for these 3 equations, they all look about the same, right? They are something reacting with something, and it's H2 and I2. On inspection, you could say, well, the rates for each of them should be the same. Well, H2 reacting with I2, that's the rate equation. It is first order in what? Yeah, hydrogen and I2. It looks simple. That's the rate equation for bromine. Okay, that's weird. This one, you need light or it doesn't even happen. You can take hydrogen, iodine, put them in a jar. This was a very sophisticated way of mob hit. You take hydrogen and chlorine and put them into a room, keep it in the dark, it's fine. Then you open it to light, and you get this bomb that goes off that produces HCl gas. It is great. Everybody dies, and then it dissolves everything. It's wonderful. Again, you need UV. So sunlight's good. There's certain kinds of LED that might kick it off. Are you looking for notes?
No,
Okay. No, it's all good. But yes, again, one more pitch. Come to chemistry class. News you can use, guys. Okay. So, but point is, depending on what species is involved, even though the state functions we're talking about, 2 things becoming something else, gases reacting with gases, fundamentally different paths. The reason why is because there are 4 things we must talk about to explain how we go from a starting material to a product. We have what are called the overall reactions. That's what we've been really dealing with up until now. Overall reactions are the balanced chemical equations, which are just the sum of stuff going in and stuff going out. Okay? It's just the balanced chemical equation. It's the summary. The reaction mechanism is the play-by-play. It's the step-by-step process by which you go from some atoms and some bonds to new atoms and new bonds. Well, new atoms sometimes, mostly new bonds, right? We're going to talk mainly about chemical reactions, which is about replication or changing our bonding structure. We have 2 more things that can happen in mechanisms. There are intermediates and there are catalysts. Besides this definition, what is an intermediate? If you had to sort of the colloquial one, what would you call an intermediate? Well, spectator and maybe. It's something that gets, yeah, sorry, go for it.
Like formed in the middle of a reaction and then used up again?
Perfect. It is formed and then used up.
like the stuff we canceled out in the
Hess's law, exactly. You can think of it where you make it, it's a product, but in the first step it may be a product, it's a reactant in another step. So it is generated and then used up. It forms and goes away. A catalyst is the other side. It is used up and then it comes back. Okay? So the two ways to look at this, we have the overall reaction. A plus B gives us C plus D. This is the balanced chemical equation that says that this here is basically, if you're looking at the job site of all the atoms you're going to rearrange, what this tells me is I need A and B, and I'm going to get C and D. That's all. It's the total sum of everything that happens. It's the accounting of the reaction. So this is our overall. The mechanism, A plus B makes X. X plus C makes D prime. D prime plus, well, no more pluses. D prime makes D. I'm going to change that. Let's call this one Y. That's easier. So here we have step 1, step 2, step 3. And what I tell from this one is I make some material that I next use up in step 2. That gets me a new material that I use up in step 3. Overall, if I was to cancel everything out, X cancels with X, Y cancels with Y. The balanced chemical equation is whatever we get at the top. It's the overall process. The mechanism is the how. The overall balanced chemical equation is the stuff you need, starting material and product. Yeah? Oh, sorry. That's because I'm being, here. You're right. Should be like this. There. Now we're good. But again, intermediates are formed and then used up. If we had to add a catalyst to this, I would say A plus B, let's say catalyst plus A and B. The reaction happens, and maybe in this very last step, we get catalyst back. If you need something as a starting material, the reaction is not going to happen without the catalyst. You still need it. But at the end of the reaction, you get your catalyst back. That's what we define as a catalyst, because it doesn't happen unless we start with it. But guess what? We were only borrowing it. It's like the opposite of an intermediate. It still shows up and goes away. The overall balanced chemical equation, it's not on there anymore, but it balances out. So again, for the point of the mechanism, there's one awesome, everything in my apartment is made at IKEA. I still live pretty close to on campus. I am still a student at heart. You guys will get this. This is an overall reaction. The stuff you bought makes the product. The catalyst is the guy you might hire to help put it together. They show up, they better leave at the end. But this is the overall balanced chemical equation, the stuff you need. The mechanism is your play-by-play. Step 1, put this together. Step 2, do this. Everything else in between, unless you have extra screws, because they always give you extra screws, it's totally fine. These are intermediates. You should not stop here. If you're done and you have a shelf and you have an intermediate, you stole something, probably. But that's the difference between, this is the concept of what we're going to discuss as we go through these things, right? So what we have now, within this, each step we define as what's called an elementary step. It's a single step of a mechanism that we cannot reduce further. In other words, without this step, there is no intermediate. Without this step, we can't do anything else. And what's nice about elementary steps is they're really easy to study. They behave according to nice, normal parameters. But we can't cut them further. In other words, there's no way, there's no intermediate behind whatever started here and this. It's the fundamental piece of the reaction. So every step in there of a mechanism here, each one of these is an elementary step. These are intermediates. This is the overall, right? Okay, that's where we're going to kick off today. We'll pick up with reaction mechanisms and how kinetics will help you on Monday. Oh, one quick mention, one quick thing. Remember, on Monday, we have our group exam. Make sure you get here on time so we can start. We're going to do a 15-minute at the very beginning. Have a great weekend, guys.